After having covered the notion of limits behave totally generally in the previous video, I really think it would help us solidify our understanding to do a couple of examples. So one example with a little table here and 3 different limits we're going to see if we can compute or not. I'm going to walk away entirely from our specific classes of functions for a moment, and I want us to think about if we are just given some specific functions f and g, and this table gives us information about the limit of those functions as x is approaching these different a values provided right here. For which of these things can I use my limits behave theorem to determine what the limit ought to be? And for which of these expressions am I unable to use the limits behave theorem, or am I unable to figure out what's going on with the limit? So for the first one, I've subtracted the 2 functions. For the second one, I've taken a square root of one of the functions. And for the third one, I've taken a quotient of one of the 2 functions. Take a minute, pause the video, get out some pencil and paper, and see if you are able to compute each of these using the limits behave theorem we discussed in the previous video. If so, awesome. If you're struggling with it, we'll unpause the video and we'll talk about each one in turn. So pause, and when you're done, restart the video. Now, in the first example here, adding and subtracting any 2 numbers is always fine. So this one should be really straightforward. If I want to know the limit of the function f minus g evaluated at x as x is approaching 1, all I have to do is say the limit of f as x is approaching 1 is 2, the limit of g as x is approaching 1 is 1, and 2 minus 1 is 1. So the answer here is really nice and straightforward. Now, for example number 2, we are not really allowed to use the limits behave theorem here, and yet we're still able to figure out what is going on with this particular function. What we know is that as x is approaching 4, the function g is approaching -2. And when we try to take a square root of that, that's going to be undefined. This is not a thing that is going to make sense. Therefore, we can say that that limit does not exist because this isn't even going to be a well-defined thing. We're going to be trying to approach, as x is approaching 4, g is getting closer and closer to -2. We are not allowed to take the square root of a negative number, and so this is not a thing that is going to exist. So we can't apply the limits behave theorem, but that does fall into that category of we know that this doesn't make sense, as we discussed via limits behave. When we get to this function where we have f divided by g and x is approaching 2, we know that this is actually going to be problematic, because what I want to do from limits behave is take the limit of f as x approaches 2, which is 3, the limit of g as x approaches 2, which is 0, but I can't say that this limit will just be equal to 3 divided by 0. I'm not allowed to divide by 0. What that means is that limits behave does not apply, and in fact, we cannot figure out what this limit ought to be without more information. It may be the case that this limit does not exist. This limit might actually exist. There are examples where we could come up with where this limit would exist, and so we just have a big fat question mark here. Limits behave does not apply, and we don't know, as opposed to limits behave does not apply, and yet we still do actually know what's going on with this limit. So these ones are harder. This one is real straightforward. Most of the time when we're working with limits behave, we're aiming to fall into this category. Let's return to those initial 4 types of functions, and let's talk about their limits at both positive and negative infinity. For the first one, I'm going to restrict my attention to polynomials because that will be a little bit easier. As our polynomials, as our x value is approaching infinity, our polynomials will be taking large numbers to high powers, and so our polynomials should be heading off to infinity, which you can see in the graphs here and here. So whenever we have a polynomial and we're going towards positive infinity, our limit will be positive infinity. However, if we're looking at a limit going towards negative infinity, it depends on if we have an odd degree polynomial or an even degree polynomial. When we take a negative number and we raise it to a power, We get a positive number if our exponent is even, and we get a negative number if our exponent is odd. So if we're dealing with a polynomial of even degree and we're looking at the limit as x is going to negative infinity, that limit will be positive infinity. If we have an odd degreed polynomial and we're looking at the limit as x goes to negative infinity, the answer will be negative infinity. And you can see examples of those in these two top graphs right here. For exponential functions, we're again going to break into two cases dependent upon the base of the exponential. If the base of the exponential function is something like e or 2, it's a number that's larger than 1. This function is going to go off towards infinity as x approaches positive infinity, and it's going to tend to 0 as x approaches negative infinity. However, over here on the right, what I've pictured for us is an exponent that has a fraction as a base, so something like 1/3 raised to the x power, and there our answers are going to flip-flop. As x is approaching negative infinity, this exponential is going to be approaching positive infinity, and as x is approaching positive infinity, you can see that our function is approaching 0. With logarithmic functions, we can easily look at the limit as x is going towards positive infinity. This one right here is a logarithm with a base like e or 2, and we see that it may happen very slowly, but our logarithm is going off towards infinity as x is going to infinity. If we were to be looking at a logarithm with a base of something like 1/3, then we can expect our function to be going off towards negative infinity here. We don't have limits for either of these functions as x is going towards negative infinity. What we have instead are limits of the function as x is approaching 0, and you can see what's happening in each of those cases here. As x is approaching 0 for this logarithm with base that is larger than 1, we're approaching negative infinity. And over here, we're approaching positive infinity as x is approaching 0. And in both cases, we're only ever approaching 0 from the right and not from the left because we are undefined in this negative territory. Last but not least, we're going to talk about trigonometric functions as x is going towards either positive or negative infinity. And for each of our trigonometric functions, these are examples of functions where the limit does not exist as x approaches either positive or negative infinity. So in fact, all trigonometric functions are periodic, meaning they have a characteristic set of behavior and this fundamental shape that we can sketch out over a particular region, and then they just repeat that pattern over and over. And so they never make up their minds and fluctuate eternally, and that means that their limits as x approaches positive or negative infinity does not exist. So that sums up all manner of sin for our 4 classes of individual functions as we're looking at limits towards positive or negative infinity. And as we continue on in the slides, we'll look at some more examples of combining polynomials at the very least, and then looking at behavior of functions as x goes towards positive or negative infinity.